Hey viewers, so we're here today to lift you up a bit and keep you hyped as we tackle the not so easy but very topic on optimization. I am Otiong.
And yours truly, Fronda, your calculus rescuers for the day.
So primarily, we want to help you guys out in formulating and solving, well, I think it's only on solving problems, right? So going back, in formulating and solving problems involving situational problems involving maximum values.
In this video, we would want you guys to appreciate and understand the simplest possible executions to one of the most important applications of calculus. Optimization!
Chad, what is optimization?
Optimization is simply using minimum and maximum in solving real-world problems.
So basically, we are going to discuss the step-by-step procedure of word problems involving optimization. Optimization is actually grounded on two theories. The Fermat's theorem, which states that if f is a differentiable function and the point a, f of a, is an extrema on f, then f prime of a is equal to 0, provided that f prime of a exists. And the extreme value theorem, which states that if a function f of x is continuous over a closed interval a, b, then f of x is guaranteed to reach an extrema on a, b.
The extrema, we mean to say minima, or the smallest possible value among all other functional values, and the maxima, which is the largest possible value among all other functional values.
Solving optimization problems is very much similar in solving simple word problems. To help you out in this lesson, here are the suggested steps in solving optimization problem. Step 1. If possible, draw a diagram of the problem. Step 2. Assign variables to all unknown quantities involved. Step 3. Identify the quantity, say Q, to be maximized or minimized. Step 4. Formulate an equation involving Q and other quantities. Express Q in terms of a single variable, say X. If necessary, use the information given and relationships between quantities to eliminate some variables. Step 5. Determine the domain or constraints of Q from the physical restrictions of the problem. The domain must be a closed and bounded interval. Step 6. Use appropriate theorems involving extrema to solve the problem. Make sure to give the exact answer with appropriate units to the question.
In this number problem, we are being asked to find two numbers whose sum is 300 and whose product is a maximum. So the first step is to write the equations describing the situation. Let's call both numbers x and y, and we are told that their sum is 300, or x plus y is equal to 300. We are also told that their product is a maximum, so a is equal to xy. We now need to solve the constraint for x or y and plug this into the product equation. We will get a of x is equal to 300x minus x squared. The next step is to determine the critical points for this equation. Now for this step, many neglect as unnecessary. Just because we got a single value, we can always assume that this will produce a maximum product. There are many methods of doing this, but in this case, we can quickly see that the second derivative of a of x is equal to negative 2. From this, we can see that the second derivative is always negative, and so a of x will always be concave down. Hence, the value must give a maximum product. Let's actually answer the question. We already have x, and now let's determine y. Y is equal to 300 minus 150, which is equal to 150. The final answer is then x is equal to 150 and y is equal to 150.
In this number problem, we are being asked to find the dimensions that will maximize the total area of the pin, having 3 partitions with 4 parts. In this figure, we can see that the pen is to be divided into 4 parts using 3 parallel partitions. Thus, we have 5 x's and 2 y's. The total amount of fencing is given to be 500 is equal to 5 times the width plus twice the length, or simply 5x plus 2y. So that we have 2y is equal to 500 minus 5x, or y is equal to 250 minus 5 halves x. We wish to maximize the total area of the pen by using the formula A is equal to width times the length, or simply A is equal to x times y. However, before we differentiate the right-hand side, we will write it as a function of x only. Substitute for y, getting A is equal to x times y. Thus, we obtain x times the quantity of 250 minus 5 halves x, or simply 250x minus 5 halves x squared. Now, differentiate this equation, getting a prime is equal to 250 minus 5 halves times 2x. Simplifying this, we get 250 minus 5x. Factoring this equation out, we get 5 times the quantity of 50 minus x is equal to 0, for x is equal to 50. Note that since there are 5 lengths of x in this construction and 500 feet of fencing, it follows that x is greater than or equal to 0, but less than or equal to 100. See the adjoining sign chart of A prime. If x is equal to 50 feet and y is equal to 125 feet, then 6,250 feet squared is the largest possible area of the pen. To sum things up, we have the Fermat's and extreme value as the basis theorem of optimization. We also have the minima and maxima.
To simplify things out, here is a hack that we would like you guys to take note of. The first step in solving optimization problems is to get 2 equations. Step 2. Plug one equation to the other and simplify. Step 3. Take the derivative of this new equation, set equal to 0, then solve.
Hi. This topic isn't that easy, right? Yet there are existing ways in simplifying and understanding the topic.
Have you all learned something? Challenge yourselves and try these questions out.
Guys, I hope we were able to save your day by sharing with you some hacks and concepts on optimization.
Check the links below for a detailed solution of our sample problems and practice problems.
And of course, don't forget to hit like and subscribe.
See you soon!
Chris and Chad signing off.